Is it?
Okay. So let us start the second talk, AGA seminar. Okay, the second speaker is Jinyan Park from the KAIST. He will talk about on the motivic cohomology of singular algebraic schemes. Okay, then you start.
Okay, thank you very much for the kind invitation, and also I'm very honored to be given a chance to speak about this recent work of mine. Before I start, by the way, let me give mentioning that it was supposed to be given in December, but there was a very tragic event that I guess most of people here know. So Professor Bomchi Kim couldn't be speaking, but instead, his topic that he was supposed to give a talk about was joint work with some other people in Korea. One is an Indian mathematician working in Korea, and the other is a Korean mathematician working in Korea. So they recently finished the work and they put them on archive, so that they are planning to give a talk about that paper, which is scheduled on the March 22nd. So if you are interested, you can go to my department website and there is going to be update about the talk. So that's going to be one advertisement which I wanted to make about. Okay, so what's going to be about because most of the people here, they probably do not know about what is called the motivic cohomology. Let me try to give us some very quick ideas about what's behind this one. So what's the idea? So here, the first thing I want to talk about is about this notion called the higher Chow cycles. And what are these guys? So the idea of this one is going to, first of all, to imitate what is already known for the topology. The topologies also already have various machines like singular homology and singular cohomology and those things. And then without looking at certain kind of smoothness assumptions, topological spaces already have these cohomology theories. So topologists can benefit a lot about the studies of those spaces from the existing theory of cohomology theory, but algebraic geometry unfortunately doesn't really have that kind of luxury. So that we have to work harder, but certain things were known already. So that's going to be probably a good idea to remind you of. So suppose K is a field, and an algebraic K scheme here just means it is a scheme of finite type over a field K. And here we do not necessarily have smoothness. So smoothness is going to be a luxury to have over here. And also we don't necessarily suppose that the scheme is reduced. So when the scheme is reduced, we call it a variety. But here the schemes could be really possibly non-separated, the scheme of arbitrary finite time. And that's going to be really, really big category. Okay, so not necessarily separated, not necessarily reduced, not necessarily smooth, of course. And so in this kind of case, what kind of machines do we have? That's really, really hard problem. But at least for the point of view of homology, we are able to do something. So here, the idea of higher Chow cycles, and this is going to be sort of like an analog of the theory of a singular homology in algebraic topology. So in algebraic topology, we deal with the topological spaces. So here, what is being done? So in algebraic topology, for instance, people talk about say the free abelian groups on say the n simple topological simplices, and then we consider continuous maps. They're not homomorphic. There's a continuous maps to some y, which is a topological space, and that's called the singular n chains. And here we have a bunch of faces and degeneracies. Like here we have bunch of maps in this direction or that direction, and they are called the faces and degeneracies, and they give you a complex basically, so that the singular homology of the topological space Y with the coefficient Z is the homology of the associated complex that this is called a singular complex, and then you take this one, and that's a singular homology. If you want to have coefficients, you can actually replace this Z by certain other rings, and that's going to be giving you series with the rings. So that's fine. On the other hand, in algebraic geometry, the trouble here is that, okay, so I can try to imitate as much as possible. So here, this topological simplex needs to replace by something algebraic. And the closest thing you can actually try is to take this delta n, which is delta n algebraic, and that's going to be spectrum of k. Say you consider a bunch of variables, and then affine space with this sum of ti is equal to 1. And then this is called algebraic simplex. It has a bunch of operations, like we have these maps, and also you have those maps as well. And using these structures, we can try to imitate. But one of the problem that we encounter is that this naively using the morphisms, where in fact the morphisms here from delta n to f to y. Suppose y is algebraic scheme, then there exists just too few morphisms. So that's going to be one of the problems that we really encounter. And also, another problem that we encounter in algebraic geometry, unlike in the algebraic topology, is that in algebraic topology, you have, if you consider continuous maps, you can still do some sort of like a small moving. That's one of the things that we learn about in algebraic topology classes. A small moving is possible without disturbing structure, but here there is no small moving. So that's going to be some problem in algebraic geometry. So this is going to be fundamentally making things much harder. So instead of using morphisms, probably the better idea is actually to use this kind of thing. So there are two modifications. First of all, we consider, basically, instead of thinking about the morphisms, we consider all cycles in the product. So if we take the product of this guy and that guy, well, morphism gives you a graph and that gives you a cycle, but that's not enough. So you consider all possible cycles on this product space over K. And then still it may have a problems. This is going to be cycles on Y cross box N. The problem is that you have a bunch of faces, but the faces do not behave nicely with the cycles because we don't have a small moving in algebraic geometry. So we consider, in fact, a smaller subgroup, the subgroup with a Y, we denote by Yn, and this is going to be the subgroup generated by cycles that intersect all faces properly. Okay, so that's going to be what we try. Then interesting thing is that, okay, so here, this fellow with a Y with this bunch of faces combined together with this boundary. So this boundary is going to be sort of like a alternating some of the faces and gives a complex. And that's normally called the simplicial version of what is called the higher Char group. And the homology of this N is denoted by this chow. Let me just use a star and yn, and this is called the higher chow group. Okay. This one, if you're not familiar with this kind of construction, then probably maybe I can give you one interesting piece of it. So when n is 0, this is going to be probably better known to you. This y0 is going to be, in fact, it's the child group, the usual child group. Sorry, not higher. The usual child group, defined initially by Wei-Liang Chow for the smooth varieties, but which is basically the cycles on y modulo the rational equivalence. Okay, so basically higher child group is going to be the one where you actually obtain by extending this one to the higher level. And we have a bunch of properties, like various properties, like localizations and etc. So that this is going to be the theory. There is also some sort of variation. So this is a sort of like alternative version. Alternative version is that. Okay, so why do we use the simplex? I mean, this one, topologically, this is the same as box. I mean, this is still the same as like a kind of S1. And this is so that algebraic geometers can also imitate this kind of idea. So instead of the algebraic simplex, what we can use also use algebraic boxes. So here the box one is, well, it would be nice actually to call it A1, but for certain technical reasons, probably people want to prefer to have this one, P1 minus 1 as the plane. So then one of the things that we can probably see is that, for instance, convenience comes out. If you consider differential form like dz over z, then it has a residue plus 1 at z is 0 and residue negative 1 at z is infinity. So that it's probably much more useful to have this kind of configuration than just naive A1. So that's a technical point. So it's still isomorphic to A1. So so combining this one several times, you can take a multiplication of this one like this, and then also you consider the phase. So these guys have a bunch of phases like 0 and infinity. Then instead of working with algebraic simplices for when n is 2, you have certain configurations like this one. So here you can have certain phases, so that you are able to define, by imitating this kind of story, this cubical version. So this is the cubical version. And one has to have a cycles modulo certain thing called the degeneracy, but I'm not going to be getting into these technical stuffs. So modulo those kind of degenerate stuff. So one of the first theorem that we know is that basically the homology we take in the simplicial version and the homology we take for this cubical version are going to be same, so that it doesn't really matter which one you take, and that's going to be convenient. And that's one of the theorems, but the important theorem that's probably more meaningful for us is this one. So theorem that I will probably call it maybe Bloch, Levin, as Grothendieck, Riemann, Rock theorem. So which means that, okay, so suppose Y is a smooth variety over a field K, then the you take this codimension Q parts of, so suppose like a Q is taken over all possible codimensions, and n is fixed over here, so n is now a fixed integer. And then operationally, it turns out that this one is isomorphic to the n's higher algebraic K-theory of Y. So roughly speaking, what this one means is that algebraic K-theory, just like any other K-theory, is going to be coming out of certain homological data of vector bundles. So if you have a variety Y, then you consider families of vector bundles of Y, and you try to manipulate certain homological construction out of it. Whereas this guy, it's going to be going sort of like digging ground, like we have a Y cross box ends, and those fellows you are looking at underground. Basically, you look at the cycles over here and then construct certain groups out of those cycles. So here, this one is going to be Y. It's something that is over this Y, the bundles. Whereas this one, you dig up the ground of Y cross box N. And magical thing is that these two guys are going to be actually isomorphic to each other up to taking tensor with Q. So that this is going to be generalization of the original Riemann log together with the Grothendieck-Riemann log. Grothendieck-Riemann was proven for n is 0, and it was generalized to such a higher level, where in fact it was claimed by Spencer Bloch in the 80s, but there was a error in one of the parts, which was called the localization theorem, and then independently, about like several years later, Mark Levine have given an independent proof without using this localization, but uses this K theory much. And then in the 90s again, Bloch gave a new proof of the localization, which fixes. So this one is going to be essentially considered to be the generalization of Grothendieck-Riemann log, proven independently by Bloch and Levine. But the limitation over here is that this is done for smooth varieties. Okay. There is one more thing. The higher Chern group is interesting because of this theorem. So it's by Vladimir Voevodsky, and again, so Y is a smooth variety over field K. Then he constructed something that he calls the motivic cohomology. So people call Voevodsky's motivic cohomology. So this is denoted by H M some star Q Y, sorry, H M star Y, Z with some different index, a double index. So he's motivic cohomology, which is defined using certain hypercohomology group of certain sheaves of complexes. And this one satisfies a bunch of universal properties. So this is going to be definitely very interesting stuff. So what's proven by Voevodsky is that under this construction, his motivic cohomology turned out to be isomorphic to Bloch's higher Chern group. So what's interesting is that this is an hypercohomology. So it's defined as a hypercohomology of certain complex of shapes. So it's a homological gadget, shape theoretic gadget, and whereas this is coming from some concrete cycle class group. So that it gives a geometric interpretation of this guy, which satisfies a certain universal property. So that the essence is that when Y is smooth over K, we have a very interesting functorial cohomology theory, which is going to be mapping into any other possible interesting cohomology theories definable for category of smooth varieties over field. So that no matter like what cohomology theory you like a complex cohomology or maybe a tall cohomology or crystalline, whichever cohomology you like, you have at least something that can map to those cohomology theories as long as you work with the smooth fellows. This one was actually further discussed in terms of what's called the motivic Atiyah-Hirzberg spectral sequence, but that's going to be generalization of the Grothendieck-Riemann log, but I don't think that's probably really necessary to talk about unless you are really familiar with Atiyah-Hirzberg spectral sequences. Okay, so pretty much I gave you the definition of something called the singular motivic, higher Chern group, and discussions about those guys for smooth fellows. But you can probably ask, okay, what about the singular case? What about the singular cases? Okay, so because you know a lot of things about smooth cases. I mean, as the algebraic geometry, of course, we know what nice things happen for smooth varieties and smooth schemes, but I mean, singularities are always kind of weird because there are so many types of singular phenomena. But at least I can actually probably say that certain singularities come from a couple of, they have a certain couple of origins. Like, for instance, there is going to sort of like a geometric singularities. Like, for instance, when y is reduced already, then if it is reduced, then you can still have some sort of like, self-intersections or maybe some kind of like this kind of cusp kind of thing. But there is also genuinely algebraic singularity of algebraic type. Like, for instance, you can have a spectrum of kt over t to the m, when m is bigger than or equal to 2. As a topological space, this is just a singleton, but it is singular because it doesn't satisfy the requirement for regularity. It's a local ring, but it's not a regular local ring. So it is a singular. One scheme could be actually everywhere singular. So that this algebraic phenomenon is going to be sort of also another contributor. This is going to be a kind of sort of like a non-reduced scheme. The non-reduced schemes could actually contribute to this one as well. Of course, if your base field K is imperfect, there is going to be also different kind of algebraic singularities as well. So, but that's a slightly different issue because there is going to be distinction between regularity and smoothness. So many people don't distinguish those guys, but that can be sort of fixable. That is a fixable in a sense by actually going to the algebraic closure. But these algebraic singularities are completely different in nature. So what would be then the idea to cope with it? Do we really even have any kind of cohomology theory if we consider the category of, say, like algebraic schemes that might contain schemes that have possibly arbitrary singularities? So that's going to be basically one of the questions one can actually ask. So the question is, can we have sort of, it doesn't have to be universal, at least a cohomology theory that is defined on the category of algebraic K-schemes. So in other words, it has to be contravariant functorial, and also when it is restricted to smooth schemes, we want it to be behaving nicely with respect to pre-existing theories. And also we want certain nice theory about like of chunk classes. And for instance, all these things could be asked. And so probably the starting point we can actually ask is whether like this one, the previous higher Char group, may work or not for the singular case. So what kind of things can go wrong with the singular case? So probably the first attempt is this, like what goes wrong if we use the above higher shell groups on these algebraic K-schemes that could possibly have arbitrary singularities and also could be arbitrarily non-reduced. Well, there are a bunch of problems you can actually have. The problem number one you can have is that, maybe I call it P1. The problem number one is that I mean, functoriality is really difficult. So here, this is a higher Char group on the smooth schemes is functorial. This comes from some, or it's not trivial, but it's doable. It's something called the moving lemma. Something called the moving lemma actually gives us this one. So this is by moving lemma. But on the algebraic K-scheme, it's not functorial. mean, proving something is not functorial is not very fun at all. You have to give a very weird counterexample to this one. But you don't really have a moving lemma over here, and then it's actually not going to be functorial. So that this appears to be the right kind of theory. Of course, if you are concerned about covariant functoriality about this, this is, when I say functoriality, is about the contravariant functoriality. We can have a pullback or not. If you are concerned about covariant phenomenon for proper morphisms, yes, this one does satisfy that. So as a covariant theory, it is functorial. So that this is why it is called sometimes motivic homology theory. But when it becomes a smooth sky, the motivic homology and motivic cohomology theory coincide. That's going to be why on the smooth varieties, you do have a proper push forward and arbitrary pullback. But if you're the singular, we don't have a pullback. And related to this non-existence of pullback structure, the problem is that then this guy, the chow something, whatever, something, something, this guy is not a graded ring on this algebraic scheme anymore. So you want some sort of a cup product structure for your cohomology theory, but if you work with this guy on algebraic scheme that might have arbitrary singularities, you don't have product structure. In fact, the product structure comes from being able to take pullback, because pullback by the diagonal map is normally the one that gives you the product structure. So this is going to be really failing. The other ones that you actually have is, okay, suppose Y is non-reduced, then by our definition, this one, the previous one, actually look at only the variety, underlying variety of a scheme. So the higher child groups that I mentioned do not distinguish Y from Y reduced. That's going to be really, really, really by definition. On the other hand, if you want something like the growth in the Riemann-Roch theorem, so comparison with this K theory, well, I don't want to actually tell you what K theory is. This is something just too complicated to bring up, but it is something that also satisfies some different kind of universal property. And the interesting thing about the K theory is that K theory is functorial, and it does distinguish Y with Y reduced. So that it is kind of, you can think of it as a kind of social problem, but sometimes this is, in fact, the source of opportunities as well. So in the 70s, 1970s, and in fact, this one was really the source of the development of the drum bit complexes and the theory of crystalline cohomology theory. And those who are working with the varieties over positive characteristics find that crystalline cohomology is really useful and also has interesting, nice properties. So you do have a discrepancy of K theory, whereas by definition, you have on the cycle side, you have this equality. That's not going to be good. So this really does tell you that you do have some issues with this one if you try to use it as is on a bigger category of schemes. So how can you capture this sort of like a missing information? I mean, this missing information. So how do you capture? How do we capture this discrepancy between Y and Y reduced? So that was, in fact, one of the questions that people have been having interest in for about 20 years ago. So that people studied, and I think it was like a blog and Ellen Anu and Kai Ruling and several people have tried to investigate this one, and by something called additive higher child groups, which I've been studying quite a long time. And then there was actually interesting result as well. But I think this one can capture possibly only certain things like the spectrum of R, T, bracket T to the M kind of things. I mean, you cannot imagine that these kind of things are only possible singularities of algebraic type in the category of algebraic schemes. That's not going to be possible. So this theory does capture some interesting phenomena, but it is going to be a little bit insufficient to cover the entire category of all algebraic schemes. So this is good for the purpose of studying the above, but not sufficient for all singular schemes. Okay, so at least this one was giving me some sort of a theorem that was actually recently published, that at least for if I consider the stuffs like Drum-bit complexes, and that's going to be in fact coming from algebraic cycles. And that's a theorem of myself with Amalandu Krishna that was only very recently published. But still, that's going to be giving us some problem. So here is going to be then the new problem that we pose. So new question, which is really about the main topic of today. So can we build a new theory that is, number one, functorial on all algebraic schemes. It looks like algebra. Okay, so maybe I will probably write this one as a scheme K. Okay, not so this one means algebraic schemes, because this notation looks like a category of K algebras. Number two, the theory restricted to the subcategory of smooth varieties coincides with the higher child group. Okay, and also we want the new theory capturing the difference between y and y reduced, and also sometimes you want some sort of like a local to global phenomena. So that's actually called the Wojciechowski descent, or maybe like if you prefer, you want something Jarisky Maya Vittoris. So you want this property, and also you want something that has the first chunk classes. And also you might want to have something that is probably a Grothendieck Riemann-Roch type theorem with the K theory. Here the K theory is algebraic, or maybe a little bit stronger version. So let me call it 6 star is going to be the motivic AGEA Hirzberg spectral sequence. So this 6 star will imply 6, but this 6 will be already very difficult. So how do you find, can you find some theory which actually builds, which actually give us a functorial theory which satisfies all these kind of things? So the my claim of today is that it's possible to have a theory that's satisfying at least up to over here. And maybe the theory I build may satisfy number 6 and 6 star as well, but yet I couldn't prove it. So what I probably try to say is that there is a new construction that is a candidate that satisfies from 1 to 5, but not yet close to the Riemann log, except for certain cases. So that highly likely it may offer some good stops over here, because so far I'm not aware of any other theory that's a functorial on all algebraic schemes that distinguishes these differences between y and y reduced and then have these properties. So I hope this is going to eventually giving me the right kind of the theory. So how do you construct such a theory? So how do we build one? Okay, so let me give a very, very quick sketch of it, because I only have about maybe 25 minutes, and that's not probably going to be a long enough time to describe everything. So it has to be very quick and concise. So as an illustration, probably let me try to do this sketch of a new approach, or sketch of a new theory in the part 1. In the special case of when y is the spectrum of say Km. So Km is K bracket T and T to the nth. Okay. So this is going to be the case when we have only algebraic singularity. So this is topologically just a singleton, so that there is no geometric singularity at all. If you cannot control this one, there is no hope for being able to do this one in general. So that I hope this is going to be probably going to be giving you some sort of convincing answer. So how do you do this one? So let me give you some idea. Basic idea behind this construction is to use some formal neighborhood in certain embeddings into certain smooth schemes. So you can think of it as sort of like a perturbations in analysis. In analysis, you probably have some issues of a function, then you try to perturb it a lot, and then there is going to be sometimes something which satisfies certain nice optimal properties, and that might sometimes give you some answers to questions. Like in Hodge theory, for instance, the harmonic forms turn out to give you the right kind of answer for decompositions. So you perturb, but the perturbation in algebraic sense is going to be not really good. So the only way you can do this one is to embed and to think about the formal label. So you can take this embedding y into, say x is an A1, which is given by a spectrum of KT. Okay, so you embed it into affine line, and then the affine line is too long, so then too big, so that you take the completion, which is going to be formal neighborhood. So this is a formal spectrum of K double bracket T. So you have, so this is your line A1, this is your Y, but it has a really, this is a really thick fact point. And over here, you now have a, oh, sorry, this is the problem with this computer is, so this is your Y, and you have now a formal neighborhood, X hat. So this is your X. So this formal neighborhood is going to be a neighborhood where I can do some geometry. So so we can do some algebraic geometry with this formal neighborhood. So why is this special? Why do you want to do this one? Well, one of the properties, technical reasons why we actually want to do stops with X hat is that, so here the point is that y is singular, but if you take the completion, if you embed into smooth sky and take the completion, Then this is a formal scheme which has a higher dimension than Y is, higher Coulomb dimension. But at least good thing is that this is a regular ringed space. So regular here means that, well, maybe I'll say regular locally ringed space. It's a locally ringed space, just like every formal scheme is. But regular means that if you look at the local ring is going to be actually becoming a regular local ring. And you know that from the commutative algebra, regular local ring is really the source of everything that we know about the homological algebra. Like if you have an arbitrary module that is coherent, you can actually take a resolution by Ausland Buchsbaum, because the rings are going to be regular. So this allows us to do some homological algebra. Singular case, the homological algebra breaks down, but XZ is regular, so you can do something. But that's not going to be enough for us. You also had in a higher theory, instead of this guy, this is bad because this is a singular, still singular. But here you have now, you can take this product with the boxes. And what's interesting is that this fellow is again taken, the product is taken in the formal scheme category. And what's really interesting is that, okay, here, what you get is going to be the spectrum of this fellow with the polynomial variables y1 to yn. Whereas here, this is a fiber product in the category of formal schemes. So that what you actually get is not just a polynomial over this guy, but the restricted formal power series. This is a subring of this is a full formal power series ring. And this is going to be the subring of convergent formal power series. And this is really interesting because if you try to localize at t is 0, then you get K Laurent series and also still this, the restricted formal power series. And this one was what John Tate called Tate's algebra. And this is non-Archimedean discrete valuation field. So it really gives us some sort of a new analytic flavor to algebraic geometry. The motto over here is that if you try to analyze certain singularities in algebraic geometry, then you make the problem a little bit more like, harder in the sense that you go to certain formal neighborhood, and in the formal neighborhood, you are able to have some higher guys. This is no longer algebraic, but this is going to be analytic in a sense, and then you are able to do certain rigid analytic geometry, so that smooth and some rigid geometry offers some machines in analyzing certain singular phenomena. So that's going to be probably the interesting point I really wanted to make over here. So, so in fact, similarly, it is possible to imitate the definition of the higher Cherenkov for affine formal scheme. So if I have, this is an Noetherian affine K formal scheme, then it is possible to define this kind of, this is going to be the cycles on this formal scheme with the box. And here again, you are having convergent formal power series. So it is some algebraic geometry using some formal power series. Here I have to have some sort of like a nice extra properties, like a proper intersection with the faces. So it is only cycles subject to proper intersections with the faces, but also, and also the proper intersections with what we call the special fibers. those who are not really familiar or who are not really friendly with the formal schemes always get confused. I mean, the formal scheme look like a scheme. It's just inverse limit of a scheme. What's the difference between scheme and formal scheme? Well, sometimes as a ring theoretical point of view, they are not really different. But genuine difference between the formal scheme and the scheme is that the formal schemes have always, at least in the Noetherian case, has some ideal called the ideal of definition. So if you take the quotient by that idea, then a formal scheme is turned into a usual scheme. And it doesn't change the topological space. The scheme and formal schemes have the same underlying topological spaces, whereas the formal schemes have extra thickness, so that you are going to be naturally having some things called the special fibers that are actually given by the underlying schemes. Okay, so you try to use this kind of thing to construct the new theory. Okay, but then you might ask, those who are actually familiar with the formal schemes may probably ask, okay, so you try to understand this wide spectrum of k bracket t to the m, and then you try to use x hat, which is a formal spec of k double bracket t. But this guy is independent of choice of this m. I mean, I might probably have like a degree m thickness. You might probably have degree m prime thickness, but they both have the same formal neighborhood. How do you then use this x hat kind of thing? And then you claim that you are trying to be able to distinguish km with km prime. So the issue that is legitimate is that, okay, so you have ym, for instance, is a spectrum of km, which is a spectrum of k bracket t, t to the m. And if I have ym prime, the spectrum of km prime with m is different from m prime, then they have the x hat is common for both of them. So this taking zq x hat n is not enough. Okay, so this is going to be certainly something that you will notice. So what should I then do? That's going to be a very important point of this construction. So I have about 10 minutes, so let me give you this stuff. So one can actually think about various coherent algebras. So these guys are coherent O x hat box and algebras such that these guys have the associated cycles inside of this cycle group. That's okay, fine, just using the usual algebraic discussions. But I can actually define this notion. Suppose we have, furthermore, this one. So A1 tensored. So this is a coherent algebra. So tensored with all y cross box n. So the pullbacks are going to be isomorphic as algebras. Then this is going to be capturing some stuffs about this one. So as all y cross box n algebras. If we do have this, then we say A1 is equivalent to A2 modulo y. So that basically you are right, because this is going to be not capturing anything about the y, because you may have a different layers of thickness, but you can try to define a new relation. So define is relations, the x at yn to be the cycles that are actually defined by as a difference between those two fellows when you have A1 is equivalent to A2. So that and define the quotient. This one is defined to be ZQ x at n and MQ x at yn. And this one is giving me a complex that one can see. So define the child Q x at mod y n to be the homology of this new complex. So this is going to be new candidate. So new candidate for KM, spec KM. So is this really good? So you can justify new definition only by presenting some useful theorems. So the theorem, which is myself, but it's on archive, but it's being evaluated somewhere. So suppose K is a field, an arbitrary field, with the cardinality is sufficiently large. Then, for this theory to be nice, you have to have a certain minimal properties. You have the graph map from something called the Miller K theories, and that's going to be, in fact, giving me the graph. And this is, in fact, the isomorphism of the groups. And this is actually very important because it's a cornerstone of the development of theories. So when M is 1, it was really a theorem of Totaro a long time ago when he was a student. And that's also done by Nestorenko and Suslin. So and that was really the first piece of the information. So if any theory that is proposed violates this theorem, then that's not a good theory. So at least this one indicates that the theory that was built over here is sound. Okay, but it's just a single case. I mean, what about the higher codimension case, and what about like how all the other kind of schemes? And not all the schemes that look like this. So the last remark about this the thing is then, okay, so if Y is an algebraic scheme in general, then what do you do? And this is actually a very difficult question, but let me indicate the idea behind this one. Okay, so here when Y is actually a scheme, they may have an arbitrary singularity, arbitrary non-reducedness, then still this is going to be having topologically a union of bunch of affine stuffs. So these UIs are affine. And it could be also singular and non-reduced. But then each of these UIs have embeddings in Xi, where Xi is smooth. So that I can take these completions in here. The completions lose information about the non-reducedness. It's going to be missing the thickness. However, it is still possible to consider a bunch of cycles over here. Okay. Once I have this, then you need to have certain cancellation of stops there so that you can actually collect the information about UI only, so that it is possible to define using the same idea, but with some quotient, some subgroup like this, so that you can actually think of this one as a ZQ Xi hat mod UIN. But this one, I'm not going to be telling you details. This requires some languages. It comes from actually the Jacob Lurie's derive the algebraic geometry a little bit, because in the previous case, we had used this kind of thing. There's a brutal force tensor product. And that's because the homological dimension of a K bracket T is 1. So you don't really have a bizarre phenomenon. But in higher dimension case, this could be as bad as you can imagine. It could be arbitrarily bad. So that just truncation is not going to be good. So you have to have, in fact, the tensor as a derived ring. So you need tensors as derived rings. So you have to work with a category of sheaves and the derived rings to be able to define this fellow. Then you still have made a choice about the cover rings, and this one does depend on the choice of a covering. So what you can still do is that, okay, you have then the coverings like this are called UIXIs. These are going to be like, let me call it curly U. Then if I have a curly V, then this is going to be a different kind of, say maybe like a ZI. Then what can I do if I have these two possible steps? Then you can have a notion of refinement, and you can use some check machine. The problem with this is that here you need some very, very new version of a moving lemma. So being able to refine this requires a new technical moving lemma on cycles on former schemes. But once you pass through this kind of technical barrier, then it is possible to find the refinement and also pass through the limit, so that you are able to define things fairly straightforwardly. So that I can define this chow. Sorry, maybe I can define, in fact, a simplified version of this yn is the homotopy colimit over U of the simplified version of this kind of U star. So let me start. Here, this homotopy colimit is taken inside the derived category of abelian shapes. But there is no OX module structure even. So this is a very, very, very large derived category, because those fellows are not coherent at all, and those fellows are not even OI modules. So that the derived category that we have to use is going to be really huge. However, it does make sense, and it is working, because this is a derived category. You can actually take the homotopy colimit, and once you have this, then you are able to use an homological machine, so that you can define this new chow of Y, and this is as a hypercohomology of the above kind of thing. And this is our definition. So just one more unit. The theorem is that this is the functorial, and this one coincides with the usual QY and for the usual for Y smooth. And there is a first chunk class, and also Zariski-Meyer Vittoris. Etc. So they have several properties in the product structures, etc. So, so this is going to be really the sketch of what was actually being done. You can probably find the preprint on an archive which I have placed, so that if you are interested, I can definitely answer your questions that you might have. Okay, let me stop the talk here. Thank you.
For the talk, is there any comments or question? Okay, I have a question. Maybe I lost your talk.
Okay.
In your space, y is maybe the non-reduced.
Not reduced.
Yeah, okay, but each irreducible component has different multiplicity. Is it allowable?
That's possibly allowed, yes. You can probably have all kind of nasty phenomena. You are allowed to have, so here I'm using, in fact, the codimension, which is not a, just for the illustration, but it's not going to really literally codimension. It is sort of like a virtual codimension in a sense. So you're allowed to have any kind of singularity and any kind of non-reducedness, right? So
But equidimensional.
So I don't suppose the y is equidimensional, but that issue can be actually taken care of. In fact, when I look at this embedding, so y may not be equidimensional, but I can actually take those guys equidimensional later, so that you can actually think about this uniform virtual codimensions. So that's going to be solving the issues. Yes.
Okay.
So could I ask a question?
Yes.
So is your child group already different from the classical child group when n equals 0 for singular variety for singular schemes?
Definitely it's different. When n is 0, so problem with the child group when n is 0 for the singular varieties is that it is not functorial. So the child group, the classical child group when n is 0 for singular varieties is different from this one because child group itself is not correct for singular varieties. Yes. So I need to fix this one. That's the issue.
I see. So already for n equals 0, your child group can already distinguish the non-reduced structure of.
Exactly, exactly. Yeah. So the classical child group is not correct for singular varieties because it is not functorial. For smooth varieties, it is functorial. So that's why. So the whole point is that I have to rebuild the theory from scratch, from everything, so that I can have a functoriality. Yeah. So it is possible to define child group for singular varieties, okay? But that doesn't mean that it is giving us the right motivic cohomology. Well, classic child group is still the right motivic homology theory, but it fails to be a motivic cohomology. That's the point. So that's what I wanted to say.
Thank you very much.
Yes, no problem.
Maybe a little bit stupid questions. Is there any examples for your cohomology theory?
Okay, so example was in fact given over here. This is probably the simplest example one can imagine because topologically it is the point and or maybe okay, so even simpler one, maybe even simpler one I can give you. Okay, so so suppose I can take a kt modulo t squared and say okay, so take this n is 1 over here, for instance, then the previous theorem actually says this one. So k2 min k2, I mean this is not really so okay, suppose even characteristic of k is 0, then this one can be decomposed into k direct sum with k cross, so that and the child group oh sorry, this is n2, so child u of 2 k22, so this is going to be the new child group. So this is isomorphism. The way I can actually tell you is that so this one captures both the norm and the trace. So for instance, okay, in algebra class or the undergraduate algebra class, suppose I have a field extension like this. It's a finite extension of field. then we know that there is a norm map from L cross to K cross, and also there is a trace map from L to K. That's what we know from algebra class. So what's interesting is that this one can actually serve for both of these guys at the same time. So that you don't need to just define these things separately. I mean, the norm and trace are going to be appearing at the same time, provided the characteristic is actually 0. So the norm and trace can be defined at the same time, because this one has a push-forward structure for the ring, so that you can actually define norm in a uniform way. But the norm over here is, in fact, this norm and that trace combined together. So that this is going to be the multiplicative part, whereas this is going to be sort of like a sort of order of vanishing one. So like if you think about the power series, then this one is corresponding to K cross, and this one corresponds to K. So that what we are doing is that modulo T squared, you are looking at this one so that it will be generalizing our understanding. So that this new cumulative motivic cumulative theory can capture both of these guys at the same time. Although it's much harder, that's a problem. I mean,
Okay,
this
thank
is
you.
the simplest one, but I don't know any other simpler one, unfortunately.
Okay. If no more questions and comment, let
Can I
us
have a quick
thanks
question?
speaker again.
Was it a question?
Yes, I was curious if y
sorry.
can be derived.
Okay, maybe there is a. Can you say it again?
So your scheme y, can you plug in derived scheme 2, and does it make a difference?
I couldn't hear you.
Can you hear me now?
Oh, yes.
Can you plug in y to be a derived scheme?
Can you why I didn't think about that kind of possibility. I mean, for me, derived stuff is going to be the sort of like temporary territory where I enter into just to work things out. But once I'm done with my purpose, I just get out because I don't want to be there. So so maybe it's possible, but I didn't think about this kind of possibility because it's for me, I'm still not very familiar with this kind of derived rings and this kind of weird world of derived stuffs. But so I don't think I will probably spend time there. But maybe it's doable, but just I don't know how to embed this derived ring into something like a formal scheme or maybe like something like that. Maybe there might be an interesting way to do this. I mean, I think there is in Taiwan, there is Adil Khan in Taiwan.
Yes.
He is working on some stuffs with derived schemes and stuff like that. So I guess he might probably know better about that world, but
Okay.
for me, it's I'm using only minimal amount of things that I need.
Cool. Thanks.
Yes.
Okay. If no question, then let us thanks speaker again.
Okay, thank you very much.
Okay. Thank you for your talk. And let us finish this round. Okay. Goodbye.